I'm going to start bringing scissors to class. It's easier that way. Okay. So if you would please turn in homework number 1, and then I've made available to you then the second homework assignment, which is due a week from today on sections 12.5 and 12.6. There's also a table that I'm hoping that we'll get to today that is available to you guys. It's either, you can either print it out for yourselves on Blackboard, or that I've put it on Blackboard, or else you can, perhaps your faculty person has made a copy for you. This is from section 12.6. All right, let's see here. Oops. Let's just put this over here a little bit. All right. Okay. All right. So what we're talking about here in 12.5 is we're looking at equations of straight lines in three-dimensional space, and then we'll be looking at equations of planes. What the most important thing about a line that I want you to remember is this, that a line, any straight line in space is determined, first of all, by a single point that it goes through and by a direction vector of the direction that the line goes to. So those are the two things that determine a line. And with that said, there are three different ways that we can write the equation of a straight line. The first thing that we had looked at last time at the end of class was called a vector equation, where this is our vector in space, a position vector, and it's equal to a certain set vector plus our parameter t times this direction vector. This v here is the direction vector. All right, so that's one way to write the equation of a line. So let's use that to go into how we can write another way of writing the line is a parametric equation. So let's suppose that our direction vector is equal to the direction A, B, and C, where A, B, and C are numbers. And let's suppose that a specific point that the line goes through is, say, x naught, y naught, and z naught. So this is our point. This is actually a position vector. This is our direction vector. And let's suppose that our general vector r is written as just plain x, y, and z. Then we can rewrite the vector equation like this. We then have an angle bracket x, y, and z equals our specific point or position vector x naught, y naught, and z naught in angle brackets, then plus our parameter t times our direction vector a, b, and c. Now, that's basically a vector equation. And so what we can do then is equate the different components. Equate the three components. All right? And so what we get then is x equals x naught plus t times a, or I could write that as a times t. Y equals y naught plus b times t. And finally, z is equal to z naught plus d times t. So we have three equations, and the parameter is t. And so we have three parametric equations. All right. Now, these three parametric equations, what we can glean from them, first of all, is that the A, B, and C right here that are multiplying the t, those are going to be, that's going to be your direction vector, okay? That's the components of the direction vector. And then this x naught, y naught, and z naught in front, that's your single point on the line. Okay. So let's look at a specific example here of getting these equations. So let's have, say, find the vector equation, EQN for equation, and parametric equations. Parametric equations of the line, and usually we use capital L to designate a line capital L, that passes through the point 513 and is parallel to I plus 4j minus 2k. All right. So we are given here, we're given a single point that the line goes through, and we're given a direction vector, because the line is parallel to this vector. And why don't we just go on and just rewrite this I plus 4j minus 2k using the angle bracket. That's going to be 1, comma 4, comma minus 2. All right. So for the vector equation, it's basically going to be something like this. R naught is going to be equal to our single point in angle bracket, 513, plus t times our direction vector, 1, 4, minus 2. Okay, so this is our direction vector. And this is a position vector of our point. Okay, so that's our vector equation. Now we can then also get from that our parametric equation. Let's just assume that R, it can be broken apart as x, y, and z. And so for the parametric, we just equate the components. Equate the components. So we have x equals 5 plus 1 times t, or just t. Y equals 1 plus 4 times t. And z equals 3 minus 2 times t. And we have our three parametric equations. Okay? Any question just on that one example? Again, from a point and a direction vector, we can get those very quickly. A little definition here. If our vector is written with the numbers a, b, and c, for instance, we can call these numbers a, b, and c the direction numbers of the line. We can call the numbers a, b, and c, quote unquote, the direction numbers. The direction numbers of capital L, the line. So just a little definition there. All right. Now, there's one last format for the equation of a line, And it's called symmetric equations of a line. And let's show how we get that. So this is C. These are called symmetric, S-Y-M-M-E-T-R-I-C, symmetric equations of a line, of L. And what we do here with these is we basically take our parametric equations, so there's the parametric equations, and we solve each one for t. So we isolate t on one side. So we take our parametric equations, and isolate t on one side. All right, so let's do that. So what we get here with the first one then is we take x minus x naught, and we divide by a. We come up with t. For the y, we take y minus y naught and divide by b. We then come up with t. And then if for the z, we take z minus z naught, divide by c, and we come up with t again. Now, the deal with these are, we've made notice that the right-hand side of all three of these equations is the same thing. It's the letter or parameter t. So if all three of these things are equal to the same thing, we can just set them equal to each other. All right? So, set equal to each other. And we get this. X minus x naught over a equals y minus y naught over b equals z minus z naught over c. Okay. And these are the symmetric equations of a line. So notice here, a couple things to notice. First of all, there's no parameter t. Okay. And then notice that the numbers in the denominator are the direction numbers. That's from A, B, C, the direction vector. And then the numbers up here, x naught, y naught, and z naught, that's from the single point that is on the line. From a single point on L. Okay. Now, the question may come up, well, wait a minute now, okay, so we divided by these direction numbers, and we got t on one side, but what if one of the direction numbers is 0? Okay, we know we cannot divide by 0. So that's really not as terrible as we might think. Let's suppose, for instance, let's just suppose b were 0. So our direction vector is a, comma, 0, comma, c. All right, that's our direction vector. All right, so we know from the parametric equation that, now this is connected with y, the b. So we know that from our parametric equation, y is equal to y naught plus b times t, right, from the parametric. Now, if b is equal to 0, therefore this becomes, if b is equal to 0, this just becomes y always equals y naught, all right? So this is the type of line where the y coordinate is always the same number, okay? So we can still write symmetric equations of this of this particular line, except we have to be a little careful when we write the y part of it. So, can still have symmetric equations. We're just going to have this. Y equal y naught, whatever that number is, comma, and then we can do the other equations here for the symmetric. We can still say, okay, x minus x naught over A equals z minus z naught over C. Okay, so part of it is written with the symmetric equation, but the y is just going to always equal y naught. All right. So let's look at another example here where we're going to look for all three types of equations. So we're going to find all three equations. And what are we told? For a line L, okay, we're told that it passes through two separate points. It passes through point A, so now we use a parentheses, 2, 4, minus 3, and point B, again parentheses, 3, minus 1, and 1. Okay, now remember, for a line, we need a point that it goes through and a direction vector. Well, here we're given 2 points that it goes through. So what do we have to find? The displacement vector, or the direction vector. So, we need to get the direction vector. Okay, this line goes from point A to point B, or you can look at it as going from point B to point A. So how do we get this displacement vector then? Any ideas? Yeah, the points of, say, the components of B take away minus the points of A. Okay, so it's going to be 3 from the B minus 2. You can go in either direction, but just be consistent. If you're going to start with B, then take away A for all of them. Minus 1, minus 4, and then 1, and then we're going to have a double minus 3. So let's simplify this. Our direction vector then is going to be 1, minus 5, and this is 1 plus 3, or 4. So that's our direction vector. Okay, now we're pretty much good to go once we have that. Now we can use either one of the points. It does not matter. I'm just going to use point A, but you could just as well use point B as your single point. So let's then look at the vector equation. Okay, it's going to be, we know it's going to be R, this vector, equals, okay, let me just write down the general form, R naught plus T times V. Well, here, let's just use for the A as our position vector here. So we put brackets here. Now we put angle brackets, because now this is considered a vector, a position vector. So we have brackets 2, 4, minus 3, all right, plus T, our parameter, and now we've got our direction vector 1, minus 5, and 4. Okay, so that's all we need for our vector equation. Then, from there, once we've got that, then yes, Jenna. We could have used B as our single point, perfectly fine. Is that your question? Yeah. Parametric. All right, so we're going to have the R is broken down into the plane X, Y, and Z. So we just equate the components. Equate the components. So we have X is equal to 2 plus 1 times t, or just t. Y is equal to 4 minus 5 times t. And z is equal to minus 3 plus 4 times t. So those are our parametric equations. And then finally over here, we can just get our symmetric equations. All right. So, and really you can just get them right off of just going from the parametric, really. Okay, so it's going to be x minus the 2 divided by, and I don't really have to put divided by 1, because this is our coefficient for the t there for the x part, equals y minus 4 all over negative 5 equals z. Now, be careful here. This is going to be z plus 3, right? Over positive 4. All right. So be careful here with this. With these symmetric equations, this here, the signs here of those numbers up in the numerator are really going to be the opposite, because we subtract in front of it. So they're going to be the opposite signs of your point, okay, your single point. And again, these numbers down here, these are your direction numbers. Okay. Does everybody get the idea here of getting all three of those equations from that information? Okay. I've got another question about this. So here's our line. On this particular line. How about this question for this line? Where does this line cross the xy plane? So let me suppose this is a question. Where, or I could say, at what point does this line, capital L, cross the xy plane? Now remember, these lines, they go all the way out to infinity one way, all the way out the other direction, okay? So, unless this line were exactly parallel to the xy plane, it's going to cross it at some point. So, you know, we're just talking here, let's put our x, y, and z here. Okay, here's our xy plane right there, and so we're talking about a line coming down, and at some point right here, it's going to cross the xy plane. All right. What can I say about the xy plane besides just how wonderful it is? Now, what can I say about the xy plane? Z is equal to 0. Exactly. At the xy plane, z is equal to 0. Any point on the xy plane, z is equal to 0. Okay. So, the best set of equations here to use for this is actually the symmetric equation. Because with the symmetric equations, we don't even have the t involved. So let's use the symmetric equation. Let me rewrite them here. X minus 2 over 1 equals y minus 4 over minus 5 equals z plus 3 over 4. All right. Now, we want to have where z is equal to 0. So I'm going to plug in 0 for that z. So let's see what we get here. X minus 2 over 1 equals y minus 4 over negative 5 equals what? Well, that's going to be 0 plus 3, or 3 over 4. Okay. So I have two equations here. I can solve for x and I can solve for y. So we can take x minus 2, well, let's just divide it by 1, and set that equal to 3/4. And so x is equal to 2 plus 3/4, which when you combine that into a fraction gives you 11/4. And then the second one, y minus 4 over negative 5, that's got to equal 3/4 also. So let's solve for y. We get y minus 4 equals what? Multiply by minus 5, minus 15 over 4. Add 4, let me go up here. Y is equal to minus 15 over 4 plus 4. And so what's that going to turn out to be? 1/4. Because 4 is 16 over 4. Get a common denominator, so that's equal to 1/4. So therefore, our question, at what point does this line cross the xy plane? Our answer is going to be this. Okay, the x value is 11 over 4. The y value is 1 over 4, and we know that the z value has to be 0. Okay. All right. So a type of question like that makes you think a little bit, because you have to understand that the xy plane occurs when z is equal to 0. All right. We're going to take just a little sidetrack here, because sometimes we're not concerned about an entire line going from here all the way to infinity over there. Sometimes we're just interested in a small part of a line. So sometimes we're just interested, just interested, we'll put it that way, in a part of a line. And the name for a part of a line is a line segment. So say we have a straight line here going all the way that way, all the way that way, and say for whatever reason we're just interested in from point A to point B. All right, and that's all we care about. All right, so let me thicken this here to make it show up a little bit more. So we just want to algebraically get an equation for that segment. Okay. So the question is, how do we describe, I'll put that in quotes, describe this line segment? All right. Let's suppose, now we're going to be using, with these lines, we use a parameter. We usually call it t. Let's say, so we have a parameter t. Let's say the way we want to do it is we want to have it, say at point A, we want to have t equal to 0, starting out at 0. And let's say we want the description to work so that at point B, our t is now equal to 1. All right, so that's how we want it to work out, and that's how you see it done in math books, etc. Okay, so let's first of all use a vector equation here to figure this out. All right. So we're going from A to B here. So we're using a vector equation. So let's have our R naught, we need an R naught, and let that equal the position vector of the point A. Position vector of point A. All right. And let another one, R1, equal the position vector of point B. Now, we then can get the direction vector going from A to B. How would we then describe the direction vector? So blank blank is our direction vector, or you could say Jordan as our displacement vector, our direction vector from point A to point B. How would we describe that in terms of R naught and R1? Here's R naught pointing to A. Here's R1 pointing to B. How do I represent this part here, this direction vector? A plus B? Well, okay. A plus this, let's do it this way. A plus this equals B. Does that make sense to you? Okay. So therefore, the direction, if A plus the vector in question equals B, let me just isolate the vector in question, and what would that then be? B minus A, or really the position vector of B minus the position vector of A. So R1 minus R naught will be our direction vector. Okay. So getting back to the vector equation then, we're going to have our position R. Okay, we're going to have our particular point R naught. This is our single point, plus our parameter T times our direction vector. And our direction vector is R1 minus R naught. We're just looking at it as going from A to B. All right. If we were going the other way, then we would transpose those. All right. So let's see what we have here then. Let's do a little basic algebra with this. So we have vector R, the general vector, the general position vector, equals R naught plus T times R1 minus R naught vectors. All right, so let's distribute this T here for a minute. So we end up getting that R arrow is equal to R naught plus T times R1 minus T times R naught. So I'm just distributing that. All right. And now let me do another bit of fiddling with this thing. Now let me combine the R naughts together into a single term. So I can go from here, R naught, our position vector in general then is equal to what? What do we have here? This R naught is multiplied by 1. This R naught is multiplied by minus T. So I could write 1 minus T in parentheses times the R naught position vector. And then I'm left with my last term plus T times the R1 vector. And then notice what we have here if we rearrange things like this. When T is equal to 0, well, this is 0, this is 0. So what we have is that our position vector then is 1 times R naught. So that's our point A. All right? And then when T goes to 1, we then have that R is equal to 1 minus 1 times R naught plus 1 times R1. And then, of course, the 1's cancel out. And we have that our position vector is equal then to R1. And that's our point B. So with this equation, as we go from A to B, And this is what I want to circle. This is really the final result for the vector, for writing it in vector form. We take our initial point, initial position vector, we multiply it by 1 minus t, our parameter. We take our final point, that position vector, and multiply it by t, and it'll work out that it'll be at those two different points when t is 0 and when t is 1. Yes, Jenna?
For the picture that you drew there, which lines are R1 and R1?
Okay. Let's pretend that this is the origin. Zeros. Let me draw a new picture. All right. Let's see here. Let's actually put this down. And let's say that up here is our segment from A to B. All right. So the position vector always, when we talk about the position vector of a point, we're always talking about it starting at the origin. So this vector right here, going from the origin to A, I'm calling R0. All right? Then the position vector going from the origin to B, I'm calling R1. And so this vector right here, representing that displacement vector, that's the difference, R1 minus the R0. Does that help at all? Okay, all right. Okay, so we looked at how we could do it with a vector. We can also, from here, we can then do it as a parametric equation. Okay, so this is our vector equation. Now let's look at doing this as a parametric equation. So remember, we're going to put that general R vector as general X, Y, and Z in the angle brackets. And that's going to equal 1 minus t. And let's see, how do I want to do this here? Okay, let's have the R0 be vector X0, Y0, Z0, okay, plus t. Now, let's put our vector or position vector R1 as X1, Y1, and Z1. All right. So what we now get, we equate the components. And we get X equals 1 minus t in parentheses times our initial X plus our terminal X value times t. Y equals, again, 1 minus t in parentheses times our initial Y plus our terminal Y times t. And then Z is equal to 1 minus t times our initial Z plus our terminal Z times t. All right. And we can represent it like that. So let me just do one single example of using the parametric equations. So let's just look at an example. Describe using parametric equations the line segment going from point A, which is 2, 4, negative 3, to point B, which is 3, minus 1, 1. Okay. So this is our X0, Y0, Z0. This is our X1, Y1, and Z1. And we just fill in the blanks here to get it. So we have x is equal to 1 minus t times 2, that's our x naught, plus, and our x1 is 3, so plus 3 times t. Y equals, or y naught is 4, so it's 1 minus t times y naught, and then our y1 is minus 1, so minus 1 times t, or just minus t. And then finally, z is equal to, again, 1 minus t times the initial z. That's negative 3. So why don't I, just to make it look better, let's put the minus sign out front and put the 3 after there. Or I could have written it also as minus 3 here. And then that's going to be plus my terminal z times t, that's plus 1 times t, or just plus t. All right. And this is for t between 0 and 1. So in this, we're just interested in going from A to B, and here t just goes from 0, point A, 1 to point B. So t is restricted here. Okay? All right. So that's all I want to say about lines. All right. So let's move on then to planes. And so let me repeat the one fact that I want to really emphasize here about lines. So this is a repeat. A line is determined by a single point and a direction vector. And this direction vector is parallel to the line. Okay. A plane is also determined by a single point. A plane is determined by a single point, but this time it's not a vector that's parallel to the plane. It's a vector that's orthogonal or perpendicular to the plane. And a vector, let's call this vector small n with an arrow over it, that is orthogonal to the plane. Or perpendicular. So just like I've been emphasizing that first fact for you guys, I equally want to emphasize this second fact for you guys. All right. Now, and we're going to show some diagrams here, and I even brought in this crazy thing that I put together at home last night. Okay. Amazing what you can use to, anyway. So I want to, first of all, give you a definition. This vector that is orthogonal to the plane is called the normal vector. So get used to that terminology. This orthogonal vector small n is called the quote-unquote normal vector. And offhand, I don't know why it's called normal, all right? But I'm sure that could be Googled and maybe something can come up on that, all right? All right, so what I want to show you here, let's get this thing up here. Okay. All right. Okay, so here we have, here's the origin, here we have the z, the x, and the y. And this blue plate here is just, of course, obviously just a part of a plane. It's a flat surface, as I said, that can basically divide the universe in half. Now, this red arrow that is coming out of the plane is the normal vector, is a normal vector to the plane. So here it is, we've got, and this black dot right here, that is a single point that's on the plane. So we've got this point, this got cut off here. This we're calling x naught, y naught, and z naught. And then from that single point is sprouting out this normal vector that is perpendicular to the plane. So we see a right angle right here between the red vector and the plane. Now, let's then pick a general point on the plane in general, and then that is this blue dot right here, and that's any other point on the plane, x, y, and z. So if we have a vector here, a direction or displacement vector from our single point to any point, we can then draw an arrow from one point to the other, and that in this case is a blue arrow. And this arrow, this vector here that you can be viewed at as sitting right on the plane, is going to be a perpendicular vector to that red normal vector. And we can do this with any point on the plane. Pick any single point, draw a vector from this given point to it. That vector is going to be perpendicular to that normal vector. Okay? So let's go to the next thing and with this. Oops, okay. So here's repeating a lot of the stuff that I just said. P naught is a single point on the plane. P, x, y, z is any other point on the plane. Now here it talks about the position vectors. R naught is the position vector of P naught. In other words, here it is. It starts there at 0, the origin, goes to an arrow to P naught. R is our direction vector from the origin to that general any point on the plane, again from the origin. So the difference of those two vectors is the displacement vector, and that's right there on the plane, okay? And so that's the difference between the x, y, z, and the x naught, y naught, and z naught, the difference in their components. That's the displacement vector. It's right there on the plane. The normal vector, I'm calling the components of the normal vector, the number a, the number b, and the number c. That's orthogonal 90 degrees to any of these vectors for any other point on the plane. Okay, so we're going to use, guess what we're going to use here? If we have two vectors that are orthogonal to each other, what type of product of two vectors can I utilize to get something in algebra? We only have had two, so you got 50-50 on this. We got the dot product and we've got the cross product. Okay, which of those two products can I use to try now to represent an algebra equation of any point on the plane? If any point is part of an orthogonal vector, which dot product can I use? Well, you 50-50, you lost. Okay, but you try. The dot product. Okay. Remember that if two vectors are orthogonal, their dot products equal what? 0, right, and that's what we're going to use. So let's go to the last of these, the slide for this one. So therefore this orthogonal vector n dot, that displacement vector from any point minus the point that we're looking at, is equal to 0. So now with the dot product we can then distribute, and that actually gives us this equation here. We can take n, or n dot r right here, we can then move n dot r naught over to the other side. So we have that. And now I'm going to put it as an algebra equation. N is A, B, and C. R is X, Y, and Z. So I know you can't see this. So we take the products of their first components, A times X, plus the second component, B times Y, plus the third component, C times Z. And that gives me some algebra. That gives me the variables on the left-hand side. The right-hand side, D, is whatever number we get from dot producting from the dot product of our normal vector times the displacement vector. So the bottom line on this is the following. And now let me get from this, let's get rid of this, and let's go over to here. Okay. All right. So, if n equaling components A, B, C, that's a general, if that is our orthogonal vector, then n dot r minus r naught is equal to 0. All right. So n is A, B, and C dot, let's call r just general X, Y, and Z. Let's call r naught X naught, Y naught, and Z naught. So dot X minus X naught, comma, Y minus Y naught, comma, Z minus Z naught equals 0. And then multiply the two, all the similar components together. We have A times X minus X naught plus B times the second component of the other, Y minus Y naught, plus C times Z minus Z naught equal to 0. And then if we collect all the like terms, this is what we get. A times X plus B times Y plus C times Z equals some number that I'm calling D. All I'm doing is collecting all the plane numbers and putting them over on the other side. This is the equation of a plane. Okay. We'll take a break in just a couple of minutes here. I want to finish this thought here. Okay, let me repeat this then. So n is our normal vector to the plane. Like we're just saying it has components A, B, and C. This is our normal vector, orthogonal vector. So we have our plane, we've got this vector, and its components are A, B, and C. All right? The equation of the plane then, and say this, then we have a single point here. Then the equation of the plane is A times X plus B times Y plus C times Z. Notice all of these coefficients of the X, Y, and Z. Those coefficients of the X, Y, and Z are directly from the orthogonal vector. All right? Coefficients are directly from the orthogonal vector. And that equals some number D. Now, how do we find out what the number D is? Well, to find out what the number D is, all I have to do, remember, To find the equation of a plane, I need a single point on the plane and its normal vector. Okay, the normal vector gives me this left-hand side of this equation. The coefficients are all from the normal vector. So the normal vector handles the left-hand side of this equation. This number D I get from the single point that's on the plane. To find out what that number D is, I plug in my single point and get D, what D is. All right? Why don't we take a 5-minute break and I'll do an example showing how this works. Okay? I don't think that one gentleman is coming back. There was an Asian guy here the first day. Do you remember? You don't even remember the other students in the class? Yeah, there was one guy here the first day. He sat in the back, but maybe you didn't notice. I don't think he's coming back. By the way, I've got the first test made up, take-home quiz made up, practice sheet all made up, ready to go. So I'm trying to stay ahead of the game here. All right. Let's look at some examples here of this. So say we're asked to find an equation of a plane that passes through the point 2, 4, -1 with a normal vector n equal to 2, 3, and 4. Okay. So, first of all, right from the normal vector, we can get the left-hand side of the equation. 2 times x plus 3 times y plus 4 times z, and it equals to some number d. Okay, we can get that right off the bat. Now, we need to get d. So for that, we use the single point that we're given. Use the single point given. So I plug that in. Our single point is 2, 4, and -1. So we have 2 times 2 plus 3 times 4, the y value, plus 4 times -1, the z value. And what do we come up with here? 4, 12, -4. So we come up with d is equal to 12. So therefore, our final answer then is 2x plus 3y plus 4z equals 12. All right? And there we have it. Equation of the plane. Everybody okay with that process? How about another kind of a reverse thing here? How about this one? Find a normal vector n to the plane given by 7x minus 4y plus 11z equals 10. So from that, what would be answer? What would be my normal vector? -7, -4, and 11 in the angle bracket. Just reading it from the coefficients of the x, y, and z. Okay? All right. Here's another kind of problem. How about find, let's get that off. How about find the equation of a plane that passes through the point let's see, P, which is 1, 3, 2, Q, which is 3, -1, and 6. So these are all points, so I'm using parentheses, and R, which is the point 5, 2, 0. Okay. Now remember that little demonstration we had in class last time. We had a point there, we had a point over there, we had a point back there. Any 3 points, as long as they're not on the same, they're not on the same line, as long as they're not collinear, any 3 points will give us a plane. They give us a triangle, and we can extend the triangle out to a plane. So we've got 3 points here. We know that there is a plane that goes through these 3 points. We want the equation of that plane. Okay, so remember, what do we need for the equation of a plane? We need a point, and we need the normal vector. So we have to work a little bit. We've gotten plenty of points. We've got 3 different points, but we have to work for the normal vector. So anybody have an idea as to how I can derive a normal vector here?
Get a direction vector, and then find a dot product, or do a dot product, and it'll give you a perpendicular vector.
Okay, all right. How about do a cross product? Because you're on the right track. First of all, you want to get 2 displacement vectors. So in other words, we've got our plane here, We've got point, point, and point, all right? So from those 3 points, I can use any 2 pairs of them to get a displacement vector there and to get a displacement vector there, all right? And then I'll have 2 vectors that are flat on the plane, or can be considered to be flat on the plane. If I take their cross product, the thing with cross products, that'll generate the perpendicular vector. Okay, so let's get the displacement vector. Let's use, now I don't have to use these, but I'm going to just use PQ and let's say PR. I could have used a different combination, so if that question comes up, I'm just got to pick something, so I'm going to use these. Okay, so PQ starts at P, ends at Q, so I take the Q components and subtract the P components. So that's going to be 3 minus 1 is 2, minus 1, minus 3, minus 4, 6 minus 2 is 4. So that's my one displacement vector. My PR starts at P, ends at R. So here I've got R, 5 minus 1 is 4, 2 minus 3 is negative 1, 0 minus 2 is negative 2. So I've got my 2 vectors that are in the plane. Now, get the cross product. So PQ cross PR, that'll give me a normal vector to the plane. So we know what do we have to do here? I, J, and K on our first row, and then let's put PQ, 2 minus 4 and 4, and PR, 4 minus 1 and minus 2. And we're going to do the 3 by 3 determinant here. Okay, so we start out, we go across that first row. Let's start with the I. And then remember, we cross out the row and the column that's in, and what we're left with is minus 4, 4, minus 1, and minus 2. Lots of minuses here. So let me not do it all in one step. Let's just see here. Minus 4 times minus 2 is a positive 8. And then we have to subtract the up diagonal. So our up diagonal is minus 1 times 4. So that's a negative. We have to subtract a negative 4. All right, we'll figure that out in just a second. Then, remember, we do minus j. So don't forget, we have to have that minus there. And let's see what we multiply that by. Cross out that first row and the middle column. And look what we have here for our 2 by 2. We have 2 times negative 2. So that's negative 4. And then we subtract. The up diagonal is 4 times 4 minus the 16. And then we do our k. That's back to being a plus. So let's cross out the row and column for that. And so we have here, 2 times minus 1. That's minus 2. And then we have a minus. And then we have 4 times minus 4 is a negative 16. Okay, let's see what we end up with here for our orthogonal vector. And I'm going to just, because it's less writing, I'm going to immediately just put it in the angle vectors. 8 double minus 4 is 8 plus 4 is 12. Now, do not forget that you have to apply that minus sign. I can see that as an error right off the bat. You got to apply that minus sign to the numbers in the parentheses. So this is negative 20, but we have a minus here, so I really have a positive 20. And then here I have, let's see, what is this? Positive 16 minus 2, that's a 14. Now what you want to do here, I really recommend, is just, let's see, is this thing really orthogonal to those 2 vectors that I started with? And we check this by using which of the 2 products? The dot product, right. So let's multiply the components here. 12 times 2, that's what, a 24. Minus 4 times 20 is a negative 80. 4 times 14 is 56, and those all add up to 0. So we're good there. Let's look at the second one. 4 times 12 is 48. Minus 1 times 20 is negative 20. Minus 2 times 14 is minus 28. And again, that adds up to 0. So we know we didn't mess up. All right? So here's our n right here. So now that's the big part of the work right there, is getting the n in this particular problem. But so now we know our n, 12, 20, and 14. So we now can generate the left side of our equation of the plane, 12 times x plus 20 times y plus 14 times 14 times 0 equals some number d. And then we can find out this number d by any one of these will end up giving us the same number d. I can pick any single point here and it'll give me the same number. Let me just plug in. So get d. I'm going to use p. So I plug in the x, y, and z values. So it's 12 times 1 plus 20 times 3 plus 14 times 2 is equal to d. So what does that come out to be? Let's see, 12, what's 60, 28. Yeah, it does come out to be 100. Oh, you're fast. Do arithmetic much better than me. So d does equal to 100. So therefore, where are we here? Yeah. So this is what I get. So 12x plus 20y plus 14z is equal to d. Now, one thing I want to point out here, is equal to 100, sorry. Let's go back to where we found our perpendicular vector n. When we did our cross product, we found out that n was equal to 12, 20, and 14. Now this is perpendicular to our plane. If those three numbers can be divided by the same number, I can get smaller numbers. And it's still going to be perpendicular to the plane. So notice, 12, 20, and 14, I think 2. I can divide them all by 2. So I could just as well have said that 6, 10, and 7 is my n. When I would have done that, let's see what happens here. This is what we got from using 12, 20, and 14. We got that it all equals 100. Well, look at what I can do here. I can divide everything on both sides of that equation by 2. So divide by 2, and I get 6x plus 10y plus 7z equals 50. Also the equation of my plane. And then notice here, this is with the normal vector 6, 10, and 7, which I could have used. All right? So sometimes we can make the arithmetic a little bit easier if all three of those numbers divide by something. Question on this particular example. All right. I want to present a fact here then. Fact. And I think this fact makes intuitive sense. Fact. Two planes are parallel if their normal vectors are parallel. Does that make sense? So let me put an asterisk so that you guys remember this fact. So basically, we've got two planes, one floating over here, one floating down here. Look at the normal vectors. that are sprouting out of each one of them, the normal vectors are either going to be pointing in the same direction or exactly 180 degrees. Either way, they're going to be parallel to each other. Okay? All right. So, normal vectors are two vectors are parallel. What's another thing we learned about parallel vectors? Two vectors are parallel if their components are blank of each other. Not opposite necessarily. In fact, two vectors are, let me just put parallel, if their components, individual components, are blank of each other. Well, let's look at these two. 12, 20, and 14 is certainly parallel to the vectors 6, 10, and 7. Multiple, scalar multiples of each other. That's what I'm looking for. If there's components, they're scalar multiples of each other. And it could be negative, but it all has to be the same multiple. All right? So therefore, two planes are parallel if their normal vectors are parallel, which means that, let me add something up here then, which means that they are scalar multiples of each other. They are scalar multiples of each other. Okay, so let's look at an example here where we can figure this out. Example. Say we're given x plus 2y minus 3z equals 4. That's an equation of one plane. And 2x plus 4y minus 6z equal to 10. Question, are these planes parallel? Okay. Well, let's see, what are their normal vectors? What's the normal? This is plane A, and this is plane B. What's the normal vector of plane A? You can read it right off of the left-hand side.
1, 2, -3.
Yeah. 1, 2, and -3. What's the normal vector of plane B? It's 2, 4, and -6. They're both scalar multiples of each other, so the planes are parallel. That means the planes are parallel. If we had these two equations, let's see what the answer would be. Given x plus 2y minus 5z equals 4, 2x plus 4y minus 6z equals 10. So it's almost like those ones that we just had. Are they parallel? Okay. What's the normal vectors of this one? Of A. 1, right? Coefficient of x, 1, 2, minus 5. That's for plane A. Now let's look at plane B. Its normal vector, just reading it right off the coefficients, 2, 4, and -6. Okay, so the first two components are scalar multiples of each other, but guess what? The third component is not the same scalar multiple. So therefore, these are not parallel normal vectors. So the third components are not the same scalar multiples. So they're not parallel. And so our planes are not parallel either. Okay. All right. So I'm hoping, so you can read a lot of stuff off of these, just off the equation of the plane. So if two planes aren't parallel, that means that they meet somewhere. They meet, all right? And they're going to intersect each other in a straight line. Not a single point, but a straight line. And let's put this down here. So let's put this as another fact here. If two planes are not parallel, they intersect in a straight line. The angle between the two planes is defined as the angle between the two normal vectors. The angle between the two planes equals the acute angle between the two normal vectors. Okay, so here we have this. Gotten from 2 ballpoint pens that I knew I would never use. So, here are our planes right here, and they are not parallel. They intersect, and where they intersect, obviously, is that crease there. It's a straight line, okay? Each of these insides of a ballpoint pen represents a normal vector to the plane, to each plane. Here's a normal vector to this plane. Here is a normal vector to the other plane. So the way that we get the angle between these two planes, if you kind of look at it through this way, we've got an angle between the two normal vectors. And that angle between the two normal vectors is the angle between the planes. We only look at the acute angle between the normal vectors, so we don't look at, which means an angle less than 90 degrees, all right? That's what acute means, less than 90 degrees. So, let's see here. Let's look at a problem. Example. Find the angle between the planes x plus y plus z equals 1 and x minus 2y plus 3z equals 1. Okay. Okay, so these planes are not parallel to each other. Their components are not a single scalar multiple of each other. So, what we have to do is get the normal vectors. Get the two normal vectors. So what's the normal vector for the first, let's call it n sub 1, for the first line? 1, 1, 1, exactly. My normal vector for the second plane 1 minus 2 and 3. We'll read it right off the equation. Okay, so now what we have to find is we have to find the angle between these two vectors. Oops. We have to find the angle between n1 and n2. So here's where that little dot product formula comes into play. So let's put here recall n1 dot n2 is equal to the magnitude of n1 times the magnitude of n2 times the cosine of the angle between the two vectors. This is a formula we all need to remember. So let's figure this out then. Okay, let's do the left-hand side here, the dot product. That's going to give us what? 1 times 1, 1 times minus 2, 3 times 1. So that's our dot product on the left. Now, what's the magnitude of n1? Well, that's going to be the square root of the sum of the squares. So that's 1 squared plus 1 squared plus 1 squared. That's the square root of 3. What's the magnitude of n2? 1 squared plus, let's see, minus 2 squared is 4, 3 squared is 9, so that adds up to, what, the square root of 14. And then times the cosine of the angle. All right, so let's see, the left side is 3 plus 1 is 4, 4 minus 2 is 2, equals the square root of, what, 42, 13 times 4, times the cosine of our angle. So let's isolate, so therefore the cosine of our angle is 2 divided by the square root of 42. So our angle is going to be the cosine inverse. Alpha is equal to the cosine inverse of 2 over the square root of 42. And we can work that out on our scientific calculator. Say we're going to round it to the nearest degree, and we get that the angle between these two is 72 degrees. Okay, that's the angle between the two planes. All right. So that's one type of problem we can do also. Now here's another kind of interesting problem connected with these same two, and that's this. Okay, it's the same two planes. Second question. Find, and I'm going to specify what type of equation we're talking about. So find symmetric equations of their line of intersection. Ooh, okay. All right, so what we're talking about here, let's go back to my little thing here. We got two planes, we got two normal vectors. This crease right here in between, this is the line that I'm talking about. And what I want to find is an equation of that straight line. And in particular, I'm asking that the equation be written in the format of the symmetric equations of the line. All right. Now, what do we need to find the equation of a line? What's the first thing we need? We need a single point on the line. So I told you that. I'm going to just drum that home to you. Need a single point on the line. What else do we need for that line? A direction vector. So for a line, we need a single point and we need a direction vector. A direction vector. Okay. Now, what I've got here with this line, so the direction vector is going to be something that goes, we just shoot that line out. It's going to be something in that direction, right? Well, notice we have these two planes, my one's flopping around here, all right? We have these two planes, and we have these two vectors that are 90 degrees to each one of these planes. Now, our line of intersection is on both of those planes. That crease there in the middle, that is on both planes. So therefore, these two vectors, normal vectors, are orthogonal to this direction vector of the line. Because remember, these vectors here are orthogonal to any vector on the plane. Well, this line is on both planes. It's where they intersect. So to find the direction vector of the line, we have to find a vector that is perpendicular, orthogonal, to both of these other vectors. Does that make sense? Now think about it a little bit. It's got to be perpendicular. This direction vector going this way has got to be perpendicular to this one and that one. Well, how do we find a vector that's perpendicular to two vectors? Which product do we use? Cross product. We use the cross product. Okay. All right, let's go back here then. So, what I had just said is this. So therefore, N1 and N2 are, well, let me put the perpendicular symbol, are perpendicular to our needed direction vector. So let's get their cross product. Get N1 cross N2 to find our direction vector. Okay, so let's do that. Let's see here. Whoa, okay, here we are way up here. This was N1 and N2. So let's do our 3 by 3, I, J, and K. N was 1, 1, and 1. And 2 was 1, minus 2, and 3. All right? Okay. So now we have to figure this out. Start with our I. Block out first row, first column. And we're going to have what? 1 times 3 minus a negative 2. So we have 3 minus a negative 2. Then let's go to our J, and we have a minus in front of it. So let's cross out the appropriate rows here, and we have 1 times 3 minus 1 times 1. 3 minus 1, and now it's a plus K. Cross out our rows and columns. We have 1 times minus 2, and then minus a 1 times 1, or 1. Okay, so let's see what we get here. I'm going to just put it in our angle bracket formula. So our first component is 3 plus 2, so it's 5. Second component, I am going to remember to multiply by that minus in front, so I get minus 2. Third component is minus 3. Now, I know that this works. I already double-checked my own arithmetic, of course, but you can check. I do encourage, especially on tests, to check by doing a dot product that the dot product with both of the vectors turns out to be 0, just to make sure. Okay, so this is our direction vector. Okay, so what do we need? We have the direction vector, but we also need a single point on the line. Now get a single point on the line. Okay, Well, let's see here now. Any ideas? Let me rewrite here these two planes that are intersecting. They are x plus y plus z equals 1, x minus 2y plus 3z equals 1. All right. So what we have to do, we have two equations, but we have three variables, x, y, and z. So therefore, there's a lot of potential, there's an infinite number of solutions. Because after all, there are an infinite number of points on a straight line. We only have to find one x, one y, and one z that satisfies those two equations. Anybody have an idea of how you can just start this with finding an x, y, z that works for both? Remember, this line's going to be going out forever. So this line's going to have any possible value of either x, y, or z as part of it, okay? So why don't I just say, hey, let's just see what happens when let's just say one of these variables, let's set them equal to 0. And then let's try to find the other two and see what we get, all right? Okay. So let's pick a variable to set it equal to 0. Which one do we want to pick? Somebody say x, y, or z. X, thank you. So let's have x equals 0. So we're going to plug in 0 there for those two equations. So what I get then is y plus z has to equal 1, and minus 2y plus 3z has to equal 1. So now I have typical algebra problem from college algebra. I have two equations, two variables. Okay, the easiest way that I find to do that is do that elimination method. Let's multiply this top equation by a number so that when we add them together, we eliminate one of the variables. So if I multiply everything by 2, that'll get rid of the y variable when I add everything together. Elimination method. So we have 2y plus 2z equals 2, minus 2y plus 3z equals 1. Let's add them together, and we get 5z equals 3, okay? Or z is equal to 3 over 5, all right? So we've got x equals 0, z is equal to 3 over 5, so now we can just find what the corresponding y is. And why don't we just use this one right up here? X is 0, z is 3 over 5, so we have y plus 3 over 5 has to equal the number 1, and so we find out then that y has to equal 2/5. Okay? So we have a single point is x is 0, y is 2/5, z is 3/5. All right. Okay, so let's see. So we've got a single point, we've got the direction. Now, what kind of line did I say we wanted? We wanted the symmetric equation of the line. So let's kind of remember what that is. That's going to be x minus x naught over the direction number equals y minus y naught over the direction number equals z minus z naught over the direction number. Okay? All right. Now, let me write again here what our direction vector is. Our direction vector that we found was 5, -2, and -3. Okay? So let's just plug in and we'll get our symmetric equation. We're going to have x minus 0, which is just x, and we put it over the direction number for x, which is a 5, equals, now y minus our y value, y minus 2/5, all over our direction number for y, which is negative 2, equals z minus our z value, 3/5, all over our direction number for z, which is negative 3. Now, if I like, I can always do some multiplying by 5 to get rid of fractions. I'm not really worried about it. This is fine as far as I'm concerned, okay? All right. Then I want to get, so we might go just a couple minutes over one other thing. I want to get finished with this section, all right? There's one last concept in this section, and it's called a formula to get the distance. We'll call it capital D, between a point and a plane. Between a point P, we'll say that P has the coordinates x naught, y naught, and z naught, and the plane, and let's say the plane has the general formula equation of a times x plus b times y plus c times z equaling d. Okay. Now, I will tell you that for the test, I'm going to not ask you to memorize this formula, but you're going to be given a list of things. I'm going to expect that you can recognize that that is the formula. Okay? All right. So this is the formula. Capital D is equal to the absolute value. We take our A coefficient, multiply it by our point x value, plus our B coefficient here and multiply it by our Y value, plus our C coefficient here, multiply it by our Z value, and then we subtract minus the D value. So I have an arrow there, minus the D value, and it's all over, so that's just the numerator, it's all over the square root of the squares of these coefficients, a squared plus b squared plus c squared. Okay. The book has a slightly different formula because what the book does is the book wants to put the d over onto the left-hand side. I like it over on the right-hand side. So that's why there is a minus here. So if you look at the book formula, it's different. So if we want to find the distance between, say, the point 1, minus 2, and 4, and the plane 3x plus 2y plus 6z equaling 5. All right, we just use our formula here. Capital D is going to equal the absolute value of, we take the x coefficient, multiply it by the x value, 3 times 1, plus the y coefficient times the y value, 2 times minus 2, plus the z coefficient times the z value, 6 times 4, and then minus the d value that's over on the other side. We do the absolute value of those combination of numbers all over the square root of the squares of the plane coefficients. 3 squared plus 2 squared plus 6 squared. Okay, so let's figure out what this is. This is 3 minus 4, so that's minus 1. 24 minus 1 is 23. 23 minus 5 is 18. So the top number is, the absolute value is the same. It's 18. The bottom number is, this is 9 plus 4 plus 36. That's 13 plus 36. That is actually the square root of 49. Well, what do you know? That's a nice, perfect square. Isn't that nice? to what we then end up having for the distance between the single point, something up here, and the plane. Do a plumb line down to the plane. This distance is 18 over 7. Okay, whatever units we're talking about. So you will be responsible for being able to implement this formula. As I said, you don't have to memorize it, but it's going to be there on the test for you to be able to recognize that, yes, that's the formula. All right. Anyway, thanks for staying over. Have a great weekend. We'll do that next section next time. So bring back this little table here, okay? Don't lose it over the weekend. Thank you.